Yeah, so I'll talk to you today about alien auroras and auroras, well, in the solar system and beyond, and the search for radio signals from distant worlds. So the aurora is the same as the northern lights, right? So I don't know, have you seen the northern lights? Last year there were northern lights in the Netherlands. I don't know if they were quite as bright as this, but anyway, they're very spectacular. So you can come to my country of Norway and you can see the northern lights. This is a good time because the solar maximum is close, so now is a good time to see the northern lights.
Wait half a year.
Sorry?
Wait half a year.
Well, the solar cycle is 11 years, so you can wait 11 years and then you can come.
Check 4 hours what?
Well, okay, you have to wait for half a year. So this is like the desert man. You have to wait half a year for the darkness. That's a very good point. For coming winter. Right. So let's think about what causes the northern lights. So there's a little video here showing the sun's interior, and you have these sort of boiling motions in this region, and those boiling motions create or amplify the existing magnetic field of the star. And sometimes this magnetic field sort of exits the stellar surface and it gradually fills up with material from the star, and then it waits a little bit. And so eventually what's going to happen in this video is that it's going to detach itself from the surface, and it sort of travels sometimes towards the Earth. So that's like shown here as a solar flare traveling towards the Earth. And then if you play the second video, when it approaches the Earth, essentially the magnetic field that's in the CME, like the global material, it interacts with the magnetic field of the Earth, which usually protects us from the solar wind. And it basically makes like the solar wind material enter into the upper atmosphere of the Earth near the poles. So first you see that they're on the day side, and then afterwards the magnetic field lines sort of connect on the back, and you get what's called the night side aurora. So you have like these two phenomena giving rise to those green bands that we saw before. But we don't just have, in our solar system, we don't just have auroras on the Earth. Oh, sorry, this first, yeah. So the aurora is, of course, what I showed before was a visible aurora. So that's what we can see with our eyes. It's usually green, but it can also be red and blue. The same sort of phenomenon also creates UV and X-ray radiation, but there's also radio waves being generated by the aurora sort of at the same time. So that's what radio signals from different worlds in the opening. So now let's look at the auroras on Jupiter. So these are in UV, so we can't really see them with our eyes, but you'll see they look quite similar to what we had on Earth. So this is also a video. Wait. There we go. It's pretty nice, huh? I think this is super cool. So this little point here, this is like Io, this is like the innermost moon of Jupiter, or it's one of the inner moons, moons of Jupiter. And essentially like, it's sort of a foot point, like the point below it on Jupiter creates this like bright point, and then you see it like this moves as Jupiter is rotating, and as the moon is moving, you see it sort of trace all that point. This is in UV, this is observed with Hubble, that's supposed to be Hubble. And the same phenomena also generates like radio emissions. So again, here you have the moon Io on the left, yeah, on the left. Jupiter is in the center, of course, and then on these lines that are shown here are magnetic field lines. So essentially on the line that connects Io to Jupiter, that's where you saw that foot point before. But it also radio emissions are also generated, and they are not emitted in every direction at the same time. They are ejected in this sort of cone. So they're a bit like, it becomes a bit like a lighthouse. So the lighthouse is always sending out its light somewhere, but only occasionally does it like sweep past where we are. So So we see these like sort of flashes of radio emissions from Jupiter. So here's like a recording of that. There's actually a sound here. I'm not sure if the sound will play. Let's try it.
Maybe that was a bit optimistic.
Alright, I encourage you to look it up. It's a sort of very spooky and whistly sound. It's not really the same frequencies that we can hear with our ears, but listening to them gave a good sense of what the signal is like. So essentially, like, this is kind of like what will take us from the solar system and into other stars, is listening for these radio auroras. So yeah, auroras on exoplanets. Did you see this piece of news? I think it's pretty exciting. There's an absolutely giant rogue planet wandering our galactic neighborhood. This is a very, very large planet. It's sort of half planet, half star, and it's 20 light years away, which is not really that. I mean, it's pretty close, but of course it's not as close as the planet, so the solar system. And it also has this aurora that was observed in radio. So this is like one example of this, admittedly super, super large planet that was also observed in radio. Then we have something that I personally worked on, is Tau Botis AB. So this was observed by people in the Netherlands. So in 2017, radio signals were observed bearing from the direction of this stellar system called Tau Botis. And people were saying, oh, could this be radio signals from the exoplanet that we know about, which is orbiting the star? These observations were made by LOFAR, which is in the Netherlands. It's near Exlu, if anybody knows where that is. I know now. And again, you have a similar situation to what we have on Earth, although this planet is much, much closer to its star. And what I did with some colleagues was that we created a computer models of the energies available to power the aurora. So we have two different simulations. One is this simulation. It looks smaller, but it's actually bigger. It sort of encompasses the star and it extends out to the planet. And then there's a second simulation that is bigger here, but it's like a planet and its environment. And by using scaling laws from the solar system, we essentially got this, basically looking at Jupiter and the other planets in the solar system. We computed that depending on the mechanism, there's like one mechanism that is very powerful, which is we call here the radiomagnetic mechanism, that could sort of explain those radio signals from tau bodies as generated in the planetary aurora. But the other mechanism, called the radiokinetic mechanism down here, it didn't generate, it wasn't sufficiently energetic, so there wasn't enough energy that we would be able to see that signal as strong as was seen by LOFAR. But then, with our model of the planet and its direct environment, we find that that model actually is much closer to what is here called the radiokinetic flux. So that's a bit bad news for us or for the LOFAR people, I don't know, because I personally no longer believe that the signal is caused by auroral emissions from the planet. However, there's another possibility that we should check out as well, which is like the final part of my talk, which is auroras on the star. So far we talked about auroras on the planet, right? But you could also have auroras on the star itself. So in this situation, it's similar to the Jupiter and Jupiter's moon system, but now the planet kind of like plays the role of Jupiter's moon, and the star plays the role of Jupiter. And on this like magnetic foot point, which connects the planet to the star, you can have this sort of hotspot that would be linked to UV as well as radio emissions. And we actually see that in our models. So this shows, on the bottom, it shows the outermost model that I was presented before, and you see these lines that connect the star and the planet. These are like the lines that have to be connected for this phenomenon to occur. So this is still a possibility that these emissions are from the star and from the planet. And once again, we have this like emission in this like cone-like structure. So this is something that we would only see part of the time, but not the whole time. I think that's my last slide. Oh yeah, and there's more to come. So here's this shows like the square kilometer array, which is this like new radio observatory being built in Australia. And this will have enhanced sensitivity, so in the future, hopefully we can observe more auroras and radius auroras from planets and their stars. Yeah, so if anybody has a question, then I'll repeat it and then I'll try to answer.
So earlier on you talked about this row of planets.
Yeah.
Is it a free-floating planet?
Yeah, that's it. Sorry, I should have been more clear on that. That's what, like, row planet is like evocative, but maybe not very clear. Like, it's a planet that has been ejected from its stellar system, so it sort of like doesn't have a star, basically. Like, this can happen if two planets get really close to each other, for example. And then you can say, what is making the radio emissions? And yeah, exactly. So it could be processes on this type of body itself, because it's not the real body that we have in the solar system, so we don't really know like everything that goes on there. But it could also be like that it has a moon, right? So it could have one or more moons, and they could be triggering this. Yes, please, in the back.
Do most planets have the magnetic field strong enough to have auroras, or is it a rare phenomenon?
Okay, so the question is whether most planets, I guess you mean in outside of the solar system as well, have a strong enough magnetic field to create this kind of effect. This is a great question, and the answer is that we don't know. We only say, that's why we often hear these type of terms like hot Jupiter or like exo-Earth and so on, because we don't really know what these planets are like. So based on like the few data points we have about the planet, we say, oh, this is like an Earth-like planet because its mass is close to that of the Earth. But often, at least for most of them, that's all we know. So there's a lot of guesswork here, and we don't really know what is like a typical magnetic field strength for a close-in hot Jupiter planet, for example. Actually, if you could observe these radio waves, that would be one of the ways to learn about the magnetic field strength of the exoplanets. So we don't know. Yeah. Yes, please.
What got you interested in studying this topic specifically?
Okay, so the question is what got me interested in studying this topic specifically. I think what I like about it is that it makes it possible. So I talked about modeling here, right? So like this is like numerical modeling, and essentially comparing the results from the numerical modeling to observations, having like a way to go sort of to connect close the loop and to connect back from what you observe to like other observables. So we are not just like speculating, but using a computer to help you with the speculation. That was a big part of it. And it's also exciting because this the new square kilometer array that's shown here being built in Australia means that like in the future we can expect more detections of this type, or at least I hope so. Yes, please.
Are they going to do more with the radio signals? Because I thought you were saying that you didn't really believe in those radio signals.
Yeah, so this is also a great question. So those observations were in 2017, right? Made with this LOFAR in the Netherlands, which is still probably the best instrument to make that kind of observation. And there have been what's called like follow-up campaigns. So it's like, I mean, you have to point the telescope, even though it's like just like a bunch of antennas on the ground, you have to like look in one direction. You can't look everywhere at the same time. So occasionally people have observed tau qualities at other times to see, oh, do we see this signal? And I could have put more of that in the slides, but there hasn't been any new reported observations that I'm aware of. Although there's a rumor that the person who did the original observations actually has more radio signals, so that's very exciting. So who knows, like, but you know, if I guess what's also interesting for me as sort of like a person who runs computer models is that if the observations are actually over the planet, that means that we are modeling the interaction properly. So it gives us like an opportunity to sort of take apart our models and be like, is it not realistic? Like which part of it is sort of wrong? And through that process, hopefully everything can be improved. And the modeling and the observations can help each other. 3 questions. Can I just look them all?
Yes,
Okay, so let's start with Lady in the cap, please.
Yes, so are we even close to predict the places and time where we can see the aurora in future or near future?
So the question is whether we can predict the aurora on Earth. Is that what you're thinking of?
Places and time, no?
Well, we can say some things about it. So there is something called an auroral forecast. If you Google it, you'll find like there's an app, like the auroral forecast app, and it does predict where the aurora will be and how strong it will be. The thing though is that to predict like into the future properly, you need to essentially to predict the weather on the sun, and it's no more predictable than the weather on the Earth, perhaps less so. So you know you have predictions, but they are not for a really long time. Just like for a few days, maybe like a week or something like that, but not like in 6 months. On Wednesday we'll have like strong aurora. There's nothing like that. And then you have the 11-year solar cycle. So when the sun is at the so-called solar maximum, so when it's more active, which is now, there will be like more auroras in general. And we have the gentleman behind.
The auroras can happen in all the range of the electromagnetic range, from radio to X-ray. But you just show, you say, I understand the first picture from the Vera-Rothstein telescope is an optical one, a single lens, a single speaker.
So you mean like in the news? I'm not the most familiar with the Vera-Rothstein telescope, do you know? So if you mean like prior to the beginning of my talk, that big picture with all the galaxies in it and so on, I think that's invisible light. But like it only shows, sorry if I'm not answering your question, you can give me a follow-up if you want, but I think it shows like items that are so far away that you wouldn't like see auroras at those scales. Like it really shows like galaxies and stars, essentially points. So I wouldn't expect, you know, the star also produces UV radiation naturally, which is why we aren't really looking for the UV signature of the aurora on the star, even though presumably it's there. We're looking for the radio, because that's expected to be a lot stronger than the star's own radio emission. So I think radio is the best like wavelength range to find these aurorae on all other stars. And then I think there was a question over here.
Yeah, actually 2 questions. My most important one is, maybe I missed something, but I did not quite understand the role of Io in the aurora for Jupiter.
Sorry, can you repeat your question?
I did not understand what you tried to explain was the role of Io in the aurora of Jupiter.
It's a little bit complicated. I probably gloss over it more than I should. But it's a good question because it now gives me the opportunity to talk about this some more. So I think this is the slide, right? So the idea here is that Io is a moon of Jupiter, right? So it orbits round and round. And the lines, these magnetic field lines, some of them are going to sort of intersecting the star, but also Io. And along those lines, there's a channel where like wave energy can propagate from Io, from the moon, and back on to Jupiter. And that is like the possibility to Jupiter's upper atmosphere that creates that like bright blue spot that we saw in the little video. But in radio, you have a sort of, you also have emissions in radio, but they are not emitted like in every direction. So they are only emitted like in like this direction, for example. So you know, as the whole system rotates, it will either like point towards you or not, like a lighthouse. That's the sort of explanation I would give, I guess.
So it's a local concentration of magnetic field lines by the interaction with the magnetic field of the Earth.
It's like waves propagating along the magnetic field lines that are triggered by the presence of OIO. Like I mean, for example, this line, it's sort of, there's nothing disturbing it, so it's just like peaceful and stationary. But the ones that where IO sort of goes through them, they essentially are like perturbed or like sort of wiggle, and this like wiggle and travels back to the star. That's what gives that like good point. I think one more question.
Oh yeah, that the technical, but on the spectrum of the radio signals from the aurora,
Yeah.
there's some very clear bands of 7 and 21 megahertz.
Right.
We have no signal. Is that something to do with emission, or is that it absorbs in the Earth's atmosphere, or instrumental, or?
But it is like, if there are these narrow bands, I suspect this is instrumental. That would be my guess, but I'm not sure. Like, if the asteroid observer, I'm more of a volume.
Yeah, I think it's good to stop here. Let's thank our